We're going to start this video with the definition of noise as it relates to sensors. Now let's get this straight. It doesn't mean noise is the sound of cars honking their horns in a traffic jam or the sounds at a construction site. Noise is not someone else's loud music that you can't stand, and it's definitely not your mother telling you, "Get out of bed, you gotta get to school." No. We will define sensor noise as the random addition of meaningless data added to your sensor signal. In simpler terms, it's all those squiggles added to a sine wave that you see when you zoom in with the oscilloscope. We define sensor noise as stemming from sources inside your circuit, with amplifiers and ADCs being amongst the usual suspects. This contrasts with interference, which comes from sources external to your circuit. High voltage power lines and large electric motors are typical sources of electrical interference. Your sensor signal may look the same, whether it is affected by noise or interference, but the solution to cleaning up that signal is very different for noise and interference. Noise is typically expressed as a signal-to-noise ratio, SNR for short. SNR is defined as 20 times the logarithm of the voltage of the signal divided by the voltage of the noise. This slide shows a quick test with the PSOC system to pinpoint the source of noise. In this case, a 10 kHz sine wave was fed into an LM741 op-amp and the amplifier of the PSOC system. The PSOC chip amplified the sine wave flawlessly, producing the output you see in yellow. The LM741 op-amp, however, badly distorted the sine wave. This op-amp clipped the peaks of the sine wave, as you see in the light blue curve. You would not want to use it if you thought your sensor would output a 10 kHz signal. The noise contribution of op-amps is expressed as a standard normal distribution with a mean and a variance. As seen in the previous slide, op-amps contribute their own noise to your sensor system. The mean value of the noise is 0, while the variance is expressed by the formula 1 over t times the integral of t vnt squared, which is certainly not 0. Vn of t is the voltage level of the noise. Noise in a circuit depends on bandwidth, so let's back up a step and review the original engineering definition of bandwidth. I say original because these days people routinely use bandwidth to characterize an internet connection, as in, "Oh my God, this bandwidth is so lousy that it's taken me forever to access this video from YouTube." In analog terms, bandwidth is the range of frequencies, low to high, that a signal uses in a transmission device. The higher the gain, the lower the bandwidth. That can be seen in the graph in the slide. The open loop bandwidth in this circuit is 600 kHz, the frequency that the gain goes to 0. To find the closed loop gain at 40 dBs, draw a straight line at the 40 dB line until it intersects the gain curve. Move vertically down until you intersect the x-axis. The closed loop bandwidth is only 8 kHz, the value of x at that point. Because noise in an op-amp is related to bandwidth, you never want more bandwidth in a system than you need to get the sensor signal amplified. The graph on the right shows a plot of 1 over f noise, affectionately known as pink noise. The corner frequency is only 0.7 Hz, so for frequencies above that, you will pass only 10 nanovolts of noise per hertz into your sensor system. Let's recap. We define noise for you in this video. Next up, we will describe the 4 most common types of noise: Johnson-Nyquist, 1 over f, shot, and quantization.